my name is Manas, and today I'll walk you through my final project. In this project, I investigate whether a k-nearest neighbor-based collaborative filtering model performs better than general-purpose regression models in predicting whether a user will like an anime. My hypothesis is that an anime recommendation system using KNN-based collaborative filtering can more effectively predict user preference compared to standard regression approaches. The motivation for this comes from the highly personal nature of anime taste. Preferences vary significantly between individuals, making it difficult to model using global trends alone. However, anime culture is strongly structured around shared genres and themes, such as shonen, seinen, slice of life, and users often form communities around similar viewing habits. From personal experience, recommendations from people who share similar favorite anime tend to be far more accurate than the generic popularity-based suggestions. This aligns closely with the core idea of collaborative filtering. KNN works by identifying instances with the highest similarity and using them to predict unknown values. In this context, it predicts whether a user will enjoy an anime by leveraging the opinions of similar users or similar items. Because this mirrors how recommendations work in real life, I expect KNN-based collaborative filtering to outperform general-purpose regression models, whose assumptions do not align well with preference-driven recommendation tasks. The dataset used in this project is the Anime Recommendations database from Kaggle, which contains large-scale user preference data sourced from my anime list. The dataset consists of ratings from approximately 73,500 users across over 12,000 anime titles. Users can add anime to their completed list and assign a rating out of 10, and this dataset aggregates those user-generated ratings. The anime.csv contains metadata for each anime, such as unique anime ID, the anime name, genre, type, number of episodes, average community rating, and the number of members who have interacted with it. To improve data quality and reduce sparsity, I removed anime with fewer than 100 ratings, resulting in a filtered set of around 10,600 anime titles. The rating.csv file contains user anime interactions, where each row represents a user rating on an anime. Ratings are given on a scale from 1 to 10, with a value of -1 indicating that the anime was watched but not rated. Several pre-processing steps were applied. Ratings of -1 were removed. Ratings for anime not in the filtered anime list were excluded. Users with fewer than 20 ratings were removed to reduce sparsity, and duplicate ratings were eliminated. After pre-processing, the final dataset contained over 6.1 million valid ratings. From this clean dataset, I constructed a user anime rating matrix, where rows represent users, columns represent anime, and values correspond to ratings. Missing ratings were filled with zeros, resulting in a sparse matrix with approximately 9,600 anime columns. This matrix forms the foundation of the collaborative filtering models used in this project. I'll now briefly summarize the EDA and what it reveals. After pre-processing, the data contains 47,000 users, around 9,000 anime, and over 6 million ratings. Despite the scale, the user matrix is extremely sparse, with about 98% of entries missing. This is typical for recommendation systems. On average, each user rates around 131 anime, while each anime receives roughly 640 ratings. This distribution is highly uneven, following a power law pattern, and this is where a small number of users contribute to many ratings and most users contribute to relatively few. This limits direct overlap between users and affects similarity calculations. The average user rating is just over 8, indicating a strong positive bias. Users tend to rate anime they already like, leading to class imbalance. So accuracy alone in predicting whether an anime is liked would be a misleading evaluation metric. Most contained in the list are TV and OVA, and genre analysis shows that comedy, action, and adventure are the most common genres, whereas thriller, police, and josei have the highest ratings, reinforcing the idea that shared genre preferences play a key role in user similarity. However, popularity does not necessarily correspond to high ratings, suggesting that global trends alone are insufficient for good recommendations. Overall, the EDA shows 3 key challenges: extreme sparsity, rating bias, and uneven user activity. These characteristics motivate the use of KNN-based collaborative filtering, which leverages local similarity between users rather than relying on global regression patterns. Next, I conducted some hypothesis testing, and I did 3 hypothesis tests to validate whether meaningful preference signals actually exist in the data. The first was a t-test on the effect of popularity, and the results showed that popularity bias does exist and should be considered in modeling. The next was to look at the effect of genre using an ANOVA chi-squared test, and the result from this was that genre preference significantly influenced user ratings, and this is really good for similarity grouping and KNN. Next, I checked whether do similar users agree more than random users, and This was supported given the test, showing that user similarity meaningfully predicts rating agreement. The overall conclusion from this is that the dataset contains strong preference signals. Both item-level factors such as genre and popularity and user-level similarity influence ratings, providing solid statistical support for using KNN-based collaborative filtering. For modeling, I split the rating data into 80% training and 20% testing to evaluate the model on unseen interactions. Using the data, I reconstructed a anime rating matrix where rows represent users, columns represent anime, and values are ratings. Missing entries were also filled with 0. I implemented an item-based KNN filtering model using cosine similarity, which is well suited for sparse and high-dimensional data. The model was trained on the transposed rating matrix so that similarity is computed between anime rather than users, and this improves the stability at scale. To make prediction efficient, I then pre-computed the nearest neighbors for each anime, and for a given user in anime, the model predicts a rating by averaging the user's ratings for similar anime. If no such rating exists, no prediction is made. The model was evaluated using mean absolute error, or MAE, as well as root mean squared error, or RMSE, and coverage. The KNN model achieved an MAE of 0.88, indicating predictions were typically within one rating point of the true value. The RMSE of 1.28 shows that large errors exist but aren't as frequent. Finally, a coverage of 81% indicates the model can make predictions for most user anime pairs, with failures mainly occurring due to cold start cases. Overall, these results suggest that KNN-based collaborative filtering effectively captures user preference patterns in this dataset. To benchmark the KNN model, I compared it against linear regression and a decision tree regressor. The linear regression model performed the worst, with an MAE of 1.23 and RMSE of 1.57. This is because linear regression assumes a linear relationship between user ID, anime ID, and rating, even though these identifiers have no ordinal meaning. As a result, it fails to capture the preference structure. While it achieved full coverage, this came at the cost of poor accuracy, making it useful only as a baseline. The decision tree regressor slightly improved performance with an MAE of 1.2 and an RMSE of 1.54, as it can model nonlinear relationships. However, it still underperformed compared to KNN. This is likely due to overfitting in highly sparse data and the absence of any collaborative similarity mechanism. Like linear regression, it achieved full coverage but produced weaker predictions. Overall, the item-based KNN model performed the best, achieving the lowest MAE and RMSE. Although its coverage was lower at approximately 81%, this reflects realistic cold start limitations rather than poor modeling. These results support the hypothesis that collaborative filtering is better suited to recommendation tasks than general-purpose regression models. All models were evaluated using a holdout validation strategy, using an 80-20 train-test split. Each model was trained on the same training data and evaluated on the same test set, ensuring a fair and consistent comparison. To conclude, this project investigated whether a KNN-based collaborative filtering could more accurately predict user anime ratings compared to general-purpose regression models. The results clearly support this hypothesis. The KNN model achieved substantially lower MAE and RMSE while maintaining practical coverage, indicating stronger predictor performance. In contrast, linear regression and decision tree models achieved full coverage but produced significantly larger errors. This highlights their limitations when applied to sparse, high cardinality data, where user and item identifiers lack meaningful numerical structure. KNN, on the other hand, leveraged local similarity between items, closely mirroring how recommendations work in real life, where people with similar tastes tend to give better suggestions. This makes collaborative filtering particularly well suited to preference-based tasks. However, several limitations still remain. The model suffers from the cold start problem, which is where new users or rarely rated anime lack sufficient data for accurate recommendations. Popularity bias is also present, meaning highly popular anime are more likely to be recommended, and this might reduce personalization. Additionally, the use of a single train test split limits insight into performance variability. And while cross-validation could address this, it is computationally expensive and poorly suited to large, sparse recommendation matrices. Overall, this project provided valuable hands-on experience in building and evaluating recommender systems. It highlighted the trade-off between accuracy and coverage, the importance of choosing appropriate evaluation metrics, and the strengths of collaborative filtering over general regression approaches in recommendation settings. As a bonus, at the end I wanted to test out the model in an actual practical situation, and so I used it to give myself a few recommendations. First, I created a new user and included a list of different anime and my personal ratings. I then added the new user to the rating matrix. After defining a recommendation function, I was able to generate a list of recommended anime. And surprisingly, it actually worked quite well. as I do enjoy the anime recommended, and it even included things like Code Geass 2, which is the sequel to the one I already highly rated. Thanks for listening. I hope you enjoyed my project showcase.